name is Michael Carrarini, and my partner is Landon Douvlos. Our advisor was Professor Bradley Johnson, and our sponsor was Mr. Jeremy Dworshak at 3M. And our project is the correlation of nozzle and cavity pressure to part weight. And this is for the Richard J. Fazenmeyer Engineering Design Conference 2026. So our abstract, in-mold cavity pressure sensors are widely used in scientific injection molding to ensure part quality, but they increase tooling cost and complexity. Nozzle pressure sensors offer a lower cost alternative through their accuracy depends on pressure loss between the nozzle and cavity. This study evaluates the relationship between nozzle pressure, cavity pressure, and part weight under varying pressure loss conditions. A Taguchi DOE varied material viscosity, runner diameter, and cavity configuration to influence pressure drop. Pressure data and part weights were collected for polypropylene and polycarbonate, with polycarbonate results deemed inconclusive due to material and machine limitations. Normalized standard effects were used to assess sensor sensitivity relative to noise. Results for polypropylene showed correlation between both nozzle and cavity pressure with part weight, with standardized effects confirming sensitivity to process variation. These findings suggest nozzle sensors can provide meaningful insight into part quality, with effectiveness dependent on material behavior and processing conditions. So an introduction into the project. Outside of that, injection molding quality is strongly influenced by pressure behavior throughout the flow path. Understanding how viscosity and pressure loss interact enables prediction of part quality using in-process sensors. So we hypothesized that nozzle sensors can predict part quality changes within 99% accuracy as long as the pressure drop remains below 10%. We got to this conclusion by using the Hagen-Poiseuille equation, which can be seen on the left, and then we applied all those conditions to a Taguchi noise matrix DOE, with our exterior matrix holding hardware changes and our interior matrix holding process changes. That can be observed in the figure in the middle.
Quickly taking a look at the results on the right, we have nozzle pressure drop versus part weight and cavity pressure drop versus part weight. Just to briefly summarize what's going on in this graph, we have distinct groupings based on the external factors in the mold that changed the most for part weight, which were runner diameter and material viscosity, and the cavity sensor had a higher R-squared value, which meant that it correlated to part quality, part weight more efficiently. In conclusion, with other results, we have the standardized effects, where we essentially took part weight, pressure outputs, and we normalized them into one standard deviation value. And as you can see down below, the standardized effects for each sensor are shown. Viscosity is picked up better by the nozzle, while runner diameter is picked up better by the cavity. In conclusion, both nozzle and cavity pressures show inverse relationship with part weight, confirming their usefulness for monitoring part quality. We would like to thank Brian Young, Bradley Johnson, Chris and Andy, Barlett, Adam, and a few other faculty members. For future work for this project, we would like to standardize this DOE pattern and do this for multiple materials along the same injection molding science.